Hello everyone, thank you for attending this session. So my talk will be focusing on two components of the hybrid system in foil. And let me start with defining the hybrid system in foil that we develop at IMS Chips in Stuttgart. So hybrid system in foil is a technique that combines different flexible components together on the same foil. And one main component of this HySiF system is ultrathin chips, where silicon less than 50 micrometer is mechanically very flexible. And that's one key point in HySiF systems, that it combines the merits of silicon technology, the well-established technology, with printed and organic technology. So the first component is ultrathin chips. As you can see here, it's a silicon chip that can be very flexible and less than 20 micrometers thickness. And of course, you need nowadays silicon technology in order to concentrate the high performance and the high accuracy for your sensor readout. So in order to perform machine learning or say advanced signal processing, nowadays, until the development of other processors on flexible substrates, you would need the power of silicon. So that's why we also developed a packaging technology called chip film patch technology, which packages such thin chips into a very high pitch interconnection technology, so in order to replace the normal wire bonding of the silicon plastic or ceramic packages. And on the same platform, this chip film patch technology, we can also do some sensors. So resistive, capacitive, or electrochemical sensors. We have tried many sensors. So one example is this humidity sensor. It's a simple interdegraded capacitor where relative permittivity changes upon moisture absorption. And also some antennas for NFC, the well-known 13.5 megahertz on the next to this thin silicon. And also the third important part is not forgetting the active components such as the flexible transistors, but now it's only limited to the relatively low speed tasks such as switch matrixing very low at very low speeds, like 1 kilo to 10 kilohertz, for example. And it's inherently flexible, it's very thin. And here is one demo that we have integrated sensors on the top, like stress sensors, thin chips in the middle, and organic transistors in the bottom as shift registers and switching matrix. So now I will, in this talk, I will shortly explain the fabrication of the HySiF and then focus on one sensor, which is a temperature sensor. Conventional PT sensor, but developed especially for our HySiF. And then I will move on to the characterization of one silicon chip, a microcontroller chip. And then I can conclude and maybe give a future outlook for our research direction. So chip film patch technology, it's mainly a stack of two polymers. So polyamide as a flexible polymer provides the flexibility of the package, and PCP as benzocyclopentane is also spin coated. It provides reliability of our package, and also it's CMOS compatible, so outgassing problems doesn't affect the chips. And the chip here is embedded in this technique. It's a sandwich structure, and on top we can fabricate our sensors or our also organic transistors or any other active or passive component. The surface is also very smooth, so you will see also the quality of the thin films deposited or fabricated on the surface is very, doesn't suffer any degradation because of the surface. And this system could be used as a scotch tape sensor system and can be attached to any surface, in this case for temperature sensing. Also releasing from this carrier substrate, so all the fabrication is done on a rigid substrate, but then at the end you can release this system by simple mechanical release or by laser release for more accurate release. Okay, so in order to have this system for temperature sensing, we have already well-established silicon technology and silicon chips for very accurate temperature sensing. However, if you use such chips in this packaging, you will get very long and very high thermal resistance between the surface of the chip and the surface to be measured. And that will lead to inaccurate or very slow measurement or response time of the sensor on the chip. So what we can do is that we get the sensor out of the chip and fabricate it on the foil surface, and that's the other option, to have on foil. And that could also be an economic implementation when you target large area electronics or array of sensors. Yeah, so small is for fast response and also linear thermal resistance between the surface and the sensor for very accurate readouts. However, also we need to consider the parasitics between the readout in the chip and the sensor on the surface. That needs to be considered in the system design. What we have done here is very conventional to what everyone else is doing. Is two different designs have been tried out on this substrate, the serpentine and the horseshoe sensor layouts. We have tried on the design values from 80 ohm like till 50 kilo ohms in order to see what is the best for output and best sensitivity of the sensor. The limit of the resolution of the fabrication is limited by our laser direct writer, so we do conventional photolithography. It's not printed. It's using CMOS, almost CMOS processes, and the thickness of the sensor material, its PT is about 50 nanometer, and of course a very thin titanium layer for promotion, like adhesion promotion. And we achieved about 2.7 per degree Celsius of the temperature coefficient, and the mismatches between 0.4 and 0.05. The first number is for the serpentine design, and the second number is for the horseshoe design, which indicates that the horseshoe design somehow randomizes the process mismatch. So we did some experiments for different construction of the technology. So the PT sensor is directly on the silicon wafer. The PT sensor is on a PCB layer, and then the third one is a PT sensor embedded into PCB layers. And then the thermal shock was varied to establish the temperature measurements. We can see here for the first, the three curves for different setups, and the sensitivity is extracted from this raw data for different number of sensors across the whole wafer, and we can get that the lowest sensitivity of the PT is on the silicon directly. However, we get better sensitivity on PCB, which can give us a feeling that PCB is a good surface for high quality thin film components. Yeah. Moving on to the effect of thinning on the silicon chips. So here is one microcontroller that we have got from market leader Peak Micro in the United States. They are market leaders in smartwatches, microcontrollers for different applications, and we got this microcontroller and then thinned it down to about 30 micrometer in this case thickness, and then we placed it inside a ceramic package to check what is the effect on the performance. So the first effect is that we characterized the 10-bit ADC on board. It's a successive approximation ADC on board, and we have recognized that the accuracy of the ADC in terms of linearity, DNL and INL, so differential and integral nonlinearity, was not affected by chip thinning. And of course, we will need to consider also bending, so further tests could be done when bend, but we need to adjust the setup so that we do not affect the linearity by the measurement setup. The second test is that the integrated band gap reference on the chip also the microcontroller was tested in a climate chamber, and we can recognize that there is a slight drop in the slope, in the sensitivity, and after thinning, and that could be due to the defects that can propagate after the back thinning to the active region. And this temperature-dependent leakages are CTAT, so it's complementary to absolute temperature, and that might be one reason for this slope degradation. The final test that we have done is on the RC oscillators. So there is two oscillators on this microcontroller, low frequency and high frequency oscillator. And you can see that there is a offset, a static offset in the low frequency oscillator. There is a histogram test for the period jitter of the low frequency oscillator. And however, this offset for the thinned chips could be trimmed. So that offset we can compensate. However, for the RC oscillator, we find a degradation with a standard deviation and mean that this after thinning the chip, and that cannot be trimmed and needs to find a solution for that oscillator. So, and also from literature, we can see that from thinning down the chip, that might be the case in this high frequency noise. The capacitive coupling of the high frequency noise is more is more injected in the substrate in the thinned case. Yeah. So as conclusion, in this talk I have discussed two types of components. Passive one is conventional platinum temperature sensor, thin film sensor on the HySiF. It's readily available for integration with HySiF. And the second one is characterization of the impact of thinning the silicon chips on the circuits and system levels, which is relatively new, and we always the thinning of the silicon chips investigation is on the device level, but here we try to find the impact on the circuit level and the system level and the accuracy of the sensor readout. So this is an image of this two chips embedded in the chip film patch, and then placed on a flexible substrate, another flexible substrate as an interposer to operate a full system in a like a wireless sensor node with NFC communication, and also another wideband frequency operation. Yeah, thank you for your attention.